Have you ever found yourself in a home improvement project or maybe making a new garden where you're suddenly faced with geometry? Well, those are the types of problems that we're going to consider in this section. 2.3.2 deals with the area of a rectangle. Now, the formula for the area of a rectangle is very simple. Area is equal to length times width, but sometimes this will lead us to a quadratic equation, which we can solve with any one of our four methods. Example 3. A park has a rectangular area of 36,000 square yards. The width is 60 yards more than twice the length. Find the dimensions of the lot. So we're dealing with a rectangular park. I'll draw a picture of the rectangle. And we're told that the area of this park is 36,000 square yards. The width is 60 more than twice the length. So I'm going to go ahead and define my variable here. Let's suppose we can say let L equal the length of the garden. So we'll suppose that this is the length of the garden. It says the width is 60 yards more than twice the length. 60 yards more than twice the length. That is the English language representing math. The width is 60 yards more than twice or 2 times the length. So the width will be 60 more than 2 times the length. So the width here would be 60 plus 2L. Looks like I have the width a little shorter than the length, but that won't mess up our algebra. We know that the area of a rectangle is length times width, so that's going to be my governing or motivating formula. The area of this rectangle is 36,000, so I'm going to go ahead and plug that in for the area. The length we're calling L, and the width we have written as 60 plus 2L. So over here on the right side, we have length times width, but the width is written in terms of the length. That means I've got a one variable equation. At this point, it doesn't look like a quadratic equation at first. It is a quadratic equation in disguise, and we'll discover that when we distribute L. So if I multiply both of those terms by L, I end up with 60L plus 2L squared. So clearly it is a quadratic equation. Now we've got 4 different methods to choose from for solving this equation, and you can choose your favorite method that applies to this particular equation. Notice we cannot use the square root property to solve this equation because we have a linear or a variable raised to the power of 1 term. So that quick, easy method is out on this one. If I decide to either factor or do the quadratic formula, we know it needs to be equal to 0. So what I'm going to do is subtract 36,000 from both sides so that I leave that 0 behind over here on the left. And I'm going to rearrange the right side so that it's in descending order. So I'm going to start with the 2L squared term first, and then the 60L and minus 36,000. Okay. Also notice all of those terms are even numbers. So let's reduce the equation by dividing all of the terms, including the 0 over there on the left, by 2. So this gives us the equation 0 equals L squared plus 30L minus 18,000. At this point, you could either factor or apply the quadratic formula, and you could go either way on this one. You may look at that and think that the numbers are too large to factor, but let me take you through the factoring method. Since we have a leading coefficient of 1, we know that we're going to have L to the power of 1 in the first 2 spots. Because our second sign here is negative, that tells me that we're going to have 2 different signs in our binomial factors. One's going to be positive and one's going to be negative. Examining this first sign, that tells me the biggest one will be positive. So I'm going to put the biggest factor right there. So I'm looking for 2 factors of 18,000 with a difference of 30. So we could play around with our calculator. 18,000, and we could just try out several different factors. Notice 18,000 divided by 30 is 600, so we know 30 times 600 is 18,000. But I'm looking for two factors that have a difference of 30. So I'm going to test it out. Let's try 18,000 divided by 100. The two factors here are 100 and 180. They have a difference of 80, so we're getting a little bit closer. Remember, we're looking for a difference of 30. Let's try 18,000 divided by, let's try 150. 150 and 120 are the two factors there, and they do have a difference of 30, so we have found our winners. Remember, the biggest one has to be positive, so we're going to put 150 here and 120 here. Did I remember that correctly? Yes, 150 and 120. Now that it's factored, I can set each factor equal to 0 and solve for the variable. Subtracting 150 from both sides, we get a possible length of negative 150. Remembering that the length is the side of a rectangle and negative distance doesn't make sense, so we will not include that as a solution to the problem. By the way, it does solve our original equation. If I plugged it in, it would balance the equation, but it does not apply to our situation. Now, on the other hand, when I add 120 to both sides, I do get a positive number, and positive length makes sense. So we can say our length is 120. Remember that in the problem, yards were our unit of measure, so we have 120 yards for the length. We need to make sure and answer both parts of the question. So the question says, find the dimensions, plural, of the lot. Dimensions means we need to find the length and the width. Well, if the length is 120, we can plug it in for L and figure out the width. 2 times 120 is 240, and we add 60 to that to get 300. So we can make our conclusion. The length of the park is 120 yards, and the width, in case you missed that, let me show you how I did that one more time. I'm taking 120, which we found for the width, for the length, plugging it in and determining the width. So the width is 300 yards, and the width is 300 yards. Okay, now we could double check this with our calculator. We know the original area was 36,000, so let's make sure that the length times the width does give us 36,000, and it does, so our answer is correct. Let's try another example using area equals length times width that leads us to a quadratic equation. Example 4. A vacant rectangular lot is being turned into a community vegetable garden measuring 18 feet by 20 feet. So we have another rectangular lot, and it's going to measure 18 feet by 20 feet. A walking path of uniform width is to surround the garden. If the area of the garden and path combined is 624 feet, find the width of the path. So let's focus our attention on the last part of that problem. That's what we're looking for, the width of the path. So let's draw a picture to help us get a bird's eye view. We have another rectangular lot, and this is being turned into a community vegetable garden. Okay, so I've got my vegetables here. And it measures 18 feet by 20 feet. So we'll say this side is 18 feet and this side is 20 feet. Okay, now a walking path of uniform width is to surround the garden. So people have to be able to access this garden to pick the vegetables. So this path is of uniform width, okay, all the way around the garden. We don't know how wide it is, so we'll say it's X feet wide here, and it's uniform, so it's X feet wide here. If the area of the garden and path combined Okay, so remember the 20 feet by 18 feet, that was the original rectangle, but the area of the entire garden, that's the big outside rectangle, is 624 square feet. And our job is to find x, the width of the path. So let's be clear, x is the width of the path. So we need to set this up understanding that this area is that big outside rectangle. Again, our governing or motivating formula is very simple. Area equals length times width. The area of the big rectangle that we're considering is 624 square feet. So I'm going to plug that in for area. 624. Now, let's talk about the length. The original length of the rectangle was 20 feet. But remember, we have increased this length by x units on this side and x units on this side. So we could say the length of the big outside rectangle is 20 plus 2x. So we'll plug 20 plus 2x in for the length, and we're going to do the same thing with the width. Notice on our rectangle, the original width was 18 feet, but I've increased it x units this way and x units this way. So the larger dimension there is going to be 18 plus 2x. So we're going to plug that in for the width, 18 plus 2x, and then our goal is to solve this equation for x. Now, it doesn't appear to be quadratic at first, but notice when I multiply using FOIL, I will have that x squared term, which means we're solving a quadratic equation. Now, it does look like it's factored, but remember that doesn't work unless it's equal to 0. So we're going to have to FOIL this out and rearrange it and then refactor. So applying our FOIL, 20 times 18 gives us 360. The product of our outside terms, 20 times 2x is 40x. The product of our inside terms is 36x. And the product of our last terms is 4x squared. So it is definitely quadratic. Now, we can't use the square root property because we do have a linear term. So we'll probably want to either factor it or do the quadratic formula. And in that case, we need it equal to 0. So let's clean house a little bit. Let's combine our middle terms to get 76x. And then let's make sure that it's equal to 0. So we want to subtract that's 624 from both sides, and I'm going to combine it over there with the constant term. So we end up with 0 equals, and when I combine these constants, I'm also going to put this in descending order. That means I want to start with the highest power first, and then the next lowest, and then we'll combine our constants. We need to evaluate 360 minus 624, and that difference there is negative 264. Like we did before, we can reduce this a little bit. We're going to, before we factor the quadratic formula, let's divide all 3 of those terms by 4 so that our numbers are smaller and a little bit easier to work with. So we end up with x squared plus 19x minus 66. Did I do that right? Let me double check those numbers. 76 divided by 4 gives me 19, so that one was good. And then 264 divided by 4 is 66. Okay, we want to make sure we have the correct numbers there. So at this point, you can either do quadratic formula or factor. It doesn't matter. Take your pick. I'm going to go for factoring first, and if that doesn't work, then I will resort to the quadratic formula. This one, anytime you have a leading coefficient of 1, factoring is pretty straightforward. So let's determine our signs. If we look at this sign first, it's negative. So we know the signs in our binomial factors are going to be different. One's going to be positive and one's going to be negative. And this first sign tells me the biggest one is going to be positive. So I need 2 factors of 66 with a difference of 19. If they don't pop into your mind right away, you can always just play around with factors using your calculator. We're looking for factors of 66 with a difference of 19. Notice 66 divided by 3 is 22. So my two factors there are 3 and 22, and they do have a difference of 19. The biggest one has to be positive. So 22 is our biggest number, 3 is our smallest number. So that wasn't so bad. Then we're going to set each of those factors equal to 0. And notice the first one gives me a negative result. A negative number is not good for modeling length or width. But the second factor, when we set it equal to 0, does give us a positive number. Remember, x was the width of the path. That was all that the question asked for, so we have found the necessary information. We can say, therefore, the width of the path is 3 feet. Make sure you always include units with your response. Now, just to be sure that this is correct, I want to make sure that 3 is the correct solution to the equation. So I'm going to go back to the original equation and I'm going to plug 3 in for x. So we have in parentheses 20 plus 2 times 3 times 18 plus 2 times 3. I'm looking for a result of 624, and we have it, so we can be very confident that we found the right answer. So what these two examples have in common is we were using a very simple formula, area equals length times width, but in both cases, it led us to a quadratic equation, which we were able to solve by factoring. And don't forget, you could also have solved those by quadratic formula and gotten the same answer. All right, in the next section, we'll consider a new type of application.